everyone. Everyone's doing well today. So you should have just finished up your third test. Yeah, third test. There are two more tests. Each of the following tests will only cover 2 chapters because there's a little bit more information in them. And then we have the final. So we're literally coming into the last quarter of the chapter or the semester. It's going to move really, really fast here. So if you can, please just stay on top of everything. This is that like last little push where it's like, oh, just get through it, just get through it. And then you will be done with chemistry, at least for right now. So this section, this is kind of where the class really deviates from introductory chemistry. If you've already taken a chem class, it probably didn't include things on organics. We're going to talk about organics. We start with the simplest thing. So the simplest is going to be what we call hydrocarbons. And they are just like what they sound, a combination of carbons and hydrogens. They will get more complicated as we go on. We'll kind of build on the backbone of the simplest hydrocarbon. Okay, so here's a firefighter over here. He must be knowledgeable about fire codes, arson, and handling of hazardous materials. And a lot of that hazardous material is a type of hydrocarbon. So organic compounds in general. So organics chemistry, there's a whole field of chemistry called organic chemistry, and this is the study of elements that contain carbon. We classify something as being quote unquote organic when it has carbon in it. So yeah, so if you hear like something say this product is organic, unless it's under the FDA being organic, it's really just has carbon in it. Over here, we've got vegetable oil. That is a organic material, has carbons and hydrogens in it. It's being dropped into a container of water. Water we would consider to be an inorganic compound, doesn't contain carbon or hydrogen, carbon and hydrogen. So an organic compound is made up of carbon and hydrogens, but we can also have little like accessories of nonmetals like oxygen, sulfur, nitrogen, phosphorus, different halogens. Don't get freaked out by the word halogen. That's just everything in column 7, like fluorine, chlorine, bromine. It's found in a lot of products, gasoline, machines, shampoos, plastics, perfumes, makeups, food, that sort of stuff. The formulas for organic compounds are always going to be written with carbon first, followed by hydrogen, and then any other element. So there are some materials out there that contain carbon. Woo! Almost lost my entire coffee there. Oh my goodness, that would have been devastating. Okay. There are compounds out there that will contain carbon, behaving kind of as like a nonmetal. That's not organic. When the carbon is written first, that's one way to identify that it's organic. So what are some of the properties of organic compounds? Because everything we've kind of been working with thus far has been inorganic, like salts and things like that. Organic compounds are typically covalently bonded. So covalently bonded meaning the electrons are shared. It's a nice strong bond. They have low melting and boiling points. So organic compounds are usually easier to phase change. Think about like butter, for instance. Butter is a great conglomeration of organic material. It's pretty easy to melt that. Versus like table salt. I mean, you can't melt table salt. You can dissolve it in water, but if you tried to melt it on your stovetop in a pan, it's not going to do anything. Your stove won't get hot enough. Organic materials are flammable and they like to combust. So, your Yankee Candle, your grill, the furnace that heats your house. All those things are running on organic materials. And then last but not least, most of them are not soluble in water. So they will separate from water. Why? Because organic materials, not all of them, but a lot of them tend to be non-polar, and water is polar, so they won't mix. Here's a organic material in comparison to an inorganic material. So organic on the left, we have propane. Inorganic is table salt. Many inorganic compounds will have really, really high melting points. So it takes a lot of energy to burn that. Most don't burn with air. So this is a nice chart comparing sort of all the properties of something that's organic with, let's say an example, to something that's inorganic, right? You do want to know the differences between those. Okay, so identify each characteristic as most typical of compounds that are inorganic or organic. So has a high melting point. We're going to say that that's inorganic, right? Inorganic, the metal, nonmetals, salts, things like that, they need a lot of heat to melt. It's not soluble in water. Organic stuff is definitely not soluble. It has this sort of formula. You don't know what this is yet, but it's got carbons and there's hydrogen. So we'll say that's organic. Has this sort of formula. I see no carbon anywhere and hydrogen, so inorganic. Burns easily with air. That is definitely an organic material. Has covalent bonds. A lot of time our organics have covalent bonds. There are some inorganic things that have covalent bonds as well, but consistently these organics will be connected by covalent. Or rather organics. So talking about hydrocarbon. Hydrocarbons are organic compounds that will contain only carbon and hydrogen. So this is the simplest of our organics. Here, and this is the simplest of the hydrocarbons. So let's look at this guy right here. We've got, this thing is called methane. We've got a carbon. Every carbon, because it wants to form an octet through its covalent bonding, it wants to have 8 electrons around it. Every carbon will in some way make 4 bonds. Okay, so you always want to have 4 bonds sticking off of the carbon. It could be carbon bonded to 4 hydrogens, like this case, or it could be carbon single bonded to 1 other carbon and then bonded to 3 hydrogens, okay? These are both known as saturated hydrocarbons. It only contains single bonds and every carbon is sort of maxed out with the number of hydrogens. In this case with methane, carbon has 4 hydrogens. In this case, the carbons each have 3 hydrogens. The reason that they can only have 3 hydrogens is because one of their open slots for their bonding is allowing the 2 carbons to be bonded together. So in methane, carbon forms 4 covalent bonds, and this makes a tetrahedral shape. All right, so it looks like this on paper. What it actually is doing, though, is something more like this. We get that little pyramid shape because here the bonds, these electrons are 90 degrees away from each other on the paper. In actuality, they're 109. They want to get as far away from each other as they can, so they spread out in all 3 dimensions. This second thing here is called, with 2 carbons, C2H6. This is known as ethane. In ethane, each tetrahedral carbon forms 3 covalent bonds to hydrogen and 1 bond to the carbon. So here's 2 carbons. I need to connect them together. The carbons will always form like this kind of carbon chain. So as we add more carbons, you'll make a chain that occupies one of the open slots of the 4 bonds, and then we fill the hydrogens in around it to create this saturated structure. It looks something like this. So it's like 2 tetrahedral pyramids connected together. So in butane, And you will learn these names in a minute. C4H10, so there's 4 carbons. There's 10 hydrogens. It says predict the shape around each carbon atom. So each carbon atom has how many bonds? 1, 2, 3, 4. This carbon has 1, 2, 3, 4, 1, 2, 3, 4, so on and so on. All of these carbons should have tetrahedral shapes because it has 4 groups. One thing I want to point out in this drawing that we will end up going over again anyway. So these carbons, when we have a nice long carbon chain like this, the carbons at the end are known as terminal carbons. So terminal carbons are only connected to one other carbon. You see that this carbon is just bonded to a single carbon. This carbon is bonded to this carbon. So it has a remaining 3 spots to fill. 1, 2, 3. So it packs 3 hydrogens in. So terminal atoms in an unsaturated hydrocarbon will have 3 hydrogens next to it. Let's look at the central carbons though. These 2 central carbons are a little bit different. They are connected to a carbon on their left and a carbon on their right. This one is connected to a carbon on its left and a carbon on its right. So it only has technically 2 open spots, right? This is being occupied by 1, 2. So it only has 2 hydrogens attached to it. So 1 hydrogen here, 2 hydrogens here. Same thing with this one, 1 and 2. So when you are dealing with an unsaturated hydrocarbon where everything is single chain, single bonded, the terminal ones will have 3 hydrogens to complete the 4 bonds, and the central carbons will only have 2 hydrogens. And you'll see that pattern repeat itself over and over again. So a large number of carbon compounds are possible because covalent bonds between carbon atoms, such as those in hexane, C6H14, are very, very strong. So these chains, these carbon chains can get pretty long. And so we need to have some sort of systematic way of naming them, especially when these carbon chains, like this one, that's just carbon and hydrogen, this thing is called hexane, when the accessories start happening. So instead of these being hydrogens, they're other fun things. So how do we name these? Alkanes contain only carbon-carbon, carbon-hydrogen bonds. They are formed with one continuous carbon chain or chain of carbon atoms. So it will always be named by how many carbons there are. That's like the defining factor of these alkanes. The word alkane, do you see how it says the ending here is A-N-E? That, just get comfortable with the A-N-E meaning single bonds. Okay, specifically single bonds between carbons. So the ending of A-N-E, you'll see it here, A-N-E, lets us know that all the carbons are stuck together and they're only stuck together with a single bond. So we have, when we're naming alkanes, we'll use the IUPAC, or the International Union of Pure and Applied Chemistry system. So everyone in the world will name these things the same way or very, very similar. It will end in ANE, which identifies to you that the carbons are single chained. And then we use Greek prefixes to name carbon chains specifically with 5 or more carbons. So the ones that are like 1, 2, 3, 4, you just have to memorize those if you, well, I guess you have to memorize all of them if you don't know the Greek prefixes. But they will have a prefix. The prefix is telling you how many carbons in chain. Okay, so we have a prefix and then we have ANE. Let's look at some of these prefixes. Here is the list up through 10. I will test you only up through 10. The prefixes do get longer than that. So the first prefix, when we're talking about one carbon, it's meth. If it's, well, there's only ever going to be methane, okay? We're not going to have methane or methine. We'll look at that a little later. But so methane, it's a carbon and it has 4 hydrogens around it. Why are there 4? Well, because this carbon doesn't have anything to bond to, right? It doesn't have another carbon to stick to, so we're going to fill all 4 spots with hydrogen. When you're dealing with a formula, like you're trying to come up with a molecular formula, one way to do it when you're dealing with an alkane, so all single bonded methane, you take the number of carbons, you multiply it by 2, and then you add 2. Okay, so this carbon here, there's one carbon, so we multiply the carbon, so 1 times 2 equals 2, and then we add 2 for 4. That lets you know how many hydrogens are going to be in it. Let's look at ethane. So F is the prefix for 2. ANE means that they're all single bonded. There's 2 carbons, and you know that because ethane will refer to 2, right? So we take the 2 carbons, we multiply it by 2, which gives us 4, and we add 2, which gives us 6 hydrogens. Okay, let's go even all the way down to 10. So dec or decane means that we have 10 carbons. I mean, the formula is written for you here, but what if you didn't have the formula? You just had this and you needed to come up with the formula. Well, decane, you know that that's 10 carbons, all right? And then to quickly figure out the hydrogens, instead of having to like draw it out and count them all, you take 10 times 2, which gives you 20 plus 2 gives you 22, H22, okay? And that's that there. So that's a quick way to get the hydrogen number from the name. So all the prefixes, meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. So when I say, hey, propane, like you have a propane tank, you're dealing with a hydrocarbon that has 3 carbon chains. This is what you run your grill off of, right? Butane is usually found in lighters. As you move up the chain, you have more energy stored in it, okay? So our cars tend to run off a lot of this thing right here, octane, because you have 8 carbons. So when you break all of those bonds apart, because every time you break a bond, you get energy, you have all these bonds to break, so lots of stored energy. Down here, propane, ethane, methane, not quite as many bonds to break when you combust it. So you're not going to get as much energy. If we ran our cars on propane, we would have to have like a really, really big tank on the back of our car. So there's a couple ways that we can write formulas. There are the regular formula, like for instance, for this one, this would be C4H10. But we can also write something which is known as the condensed structural formula. So in the condensed structural formula, each carbon atom and its attached hydrogens are written as a group. There's a subscript that indicates the number of hydrogens, and then you put a line to show where they're bonded together. So remember when I said the carbons on the end are the terminal carbons, they'll have 3 hydrogens. That's why this is CH3 and this is CH3. The formula tells us though that we need to have how many carbons? 4 carbons chained together. So we put our terminal, we connect it to a central, and then a terminal. This is kind of a quick way to write them out instead of like having to actually stretch out all the hydrogens. So alkanes are written, we can write them either expanded or condensed. Sometimes you'll be asked to write them as condensed, and sometimes you'll be asked to write them as expanded. So this would be an expanded carbon, specifically this is a carbon at the end, right? It has 3 hydrogens, or you can write it as a condensed. So you just take this whole unit here and we write it like that. I think that's much easier. An expanded structure for a central carbon atom, there's the carbon and then the 2 hydrogens, or we can just write it as CH2 in a condensed way. That's a little bit faster. Any questions on that? I don't have anybody with their camera on today, which is fine, but I have like 0 idea if you guys are understanding this. So if you do have questions, you got to turn your mute off and ask me. Okay. Here's another way to write it. These are called skeletal formulas. In a skeletal formula, these things aren't actually here. Okay, see these CH3, CH2. Those are just sort of inferred for this, but instead, so the structure would actually look like this. And you're gonna see me draw them a lot like this because I am lazy sometimes. So the structure would actually looks like this. That is representing to you a hydrocarbon. You may be thinking, well, how am I supposed to read that? Well, the points and ends represent a carbon. So you want to think about there being a carbon here, a carbon here, here, and here. So 1, 2, 3, 4. So 4 is going to be bute. And they're all single bonded to each other. So it would be butane. These two guys at the end are terminal carbons. So you can infer that there are 3 hydrogens that are coming off. These two are central carbons. So you can assume that there's 2 hydrogens coming off. This is like the lazy man's way of writing these, but you will see this quite often. So you want to get comfortable with, okay, points and end dots are telling me that those are carbon spaces. So one thing to note is that a conformation, so a conformation of an alkane. When you are looking at a hydrocarbon that's all single bonded, so an alkane, know that at places where you have a carbon single bonded to another carbon, these things are free to rotate. Okay, when you have a single bonds, things can rotate around the single bond. So it can make the shapes of two of the same thing look different. Let me rephrase that. It can make 2 things that are the exact same, but they can look slightly different. Do you see how you've got a terminal carbon over here sitting up and a terminal carbon here sitting up? So both of those are pointing up. And over here you have a terminal carbon pointing up, and over here you have a terminal carbon pointing down. So this structure is kind of going like this: carbon, 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 carbon. This is going carbon, 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 down to carbon. Both of those are talking about the same thing. They're the exact same thing. They both have 4 carbons chained together and they're saturated and they're all single bonded. So this is butane and this is also butane. This single bond means that you can rotate freely. So I'm going to show you 2 things that are the exact same structure. I'm going to do hexane. So hexane means that I should have 6 carbons. That could be written like this: 1, 2, 3, 4, 5, 6. This is sort of how you traditionally see it, this like zigzag: 1, 2, 3, 4, 5, 6. Or it could be drawn like this: 1, 2, 3, 4, 5, 6. Okay. This is also hexane: 1, 2, 3, 4, 5, 6. Either of those are talking about hexane. You can rotate to make the shape different when it's single bonded. If it's double bonded or triple bonded, that is not true. Okay. If I was to fill in the details here, this would be CH3. This is CH2, 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 and CH3. This is CH3, CH2, CH2, H2, CH2, CH3. Okay, that gets really cumbersome to have to write all those out when I can really kind of represent it with just a skeletal stick structure. This idea though of those being the same or having these conformation shapes where the shape is different, but it's the same thing only for single bonds. Okay. So different ways we can represent our alkanes. We can write it as its formula. This is talking about hexane. So C6H14. Remember, we can get the hydrogens by taking carbon number 6 times 2, 12 plus 2 gives us 14. The extra 2 is coming because you get 3 on the ends and you only have 2 ends. So we could draw it as a ball and stick. I would never ask you to draw it as a ball and stick. That would be very cumbersome. You could do it as the expanded formula. That could be asked. It's kind of a pain because you have to write all the carbons out and then you have to put every single hydrogen, all 14 hydrogens. You could do it as a condensed structural formula, which is a little bit easier. Sometimes you'll see condensed structural formulas written like this, where it's got the kink, the zigzag, or you could see it written as a straight line. The skeletal formula will have the kinks in it. It doesn't have where like the actual carbons written out, but you have to have the kinks in it. Otherwise, you would just end up, you would never do it like this because you'd just end up with a straight line and you'd think, how many carbons are there? You need to have the kinks or the points to let you know that it is a carbon. So here's butane, C4H10. Its expanded structure formula looks like that. Its ball and stick structure looks like this. A couple different condensed structural formulas. Remember, these are all single bonded. So at any of these points, I can rotate this structure. So all of these are examples of condensed structural formulas. It could be written as a straight line. It could be written like with a kink like this. It could be written as a almost box. All these things are talking about the exact same structure. Here's some skeletal formulas. Okay. So get comfortable with looking at these things, and instead of seeing like what the shape is, at least for the single bond, just count up the carbons. 1, 2, 3, 4. 4 carbons, 4 is bute. They're all saturated in single bonded butane. Okay, so given this expanded structural formula, I want you to write its molecular formula. The molecular formula is like the C's and the H's with the subscripts. The condensed structural formula, so smush all the hydrogens with the carbon and then tell me what it is, its compound name. So write it out. You are going to have to do a lot of writing in this section with structures. So in this one, it's a lot of drawing of structures. 1, 2, 3, 4. There are 5 carbons. I'll give you all 2 minutes for that. Okay, so if we want to write the molecular formula for this, we need to count up the carbons. So this is 5 carbons. Oh, come on, C5. And then the hydrogens, well, I'm just looking at this and I can see it's saturated, like every spot that's available outside of that chain is filled with hydrogen. So I know I can take my 5, multiply it by 2 and add 2 for a total of 12. Otherwise you can count 3, 5, 7, 9, 12. The condensed structural formula, that's where we're going to group the carbon with its adjacent hydrogens. So it would be CH3 at the end, CH2 in the center, CH2, CH2, 1, 2, 3, 4. That brings me to here. And then I've got my other terminal, so CH3. The compound name, 1, 2, 3, 4, 5. 5 carbons is pent. And they're all single bonded. The carbons are all single bonded to each other and there's no like funky accessories or anything. So we can just go with pentane and we're done. Questions on that? You gotta let me know if you're not getting it. Cause I can't. No questions. Cecilia is like an organic naming expert so far. Okay. We will add more. Nope, Lyric. Okay, awesome. Thank you for the feedback. Because is it going to get more complicated than this? Yeah. All right, I want you to write the condensed structural formula for these two things. So write down ethane in your notes, write down heptane in your notes, and then I want you to write them. The condensed structural formula, remember that's where you put the carbons and the hydrogens together, and then you put a line between for however many you need, okay? So I'll give you 2 minutes for that. Okay, so when you're given a name and you're trying to write its structural formula, or if you were taking a test, it would probably be like multiple choice options where the structural formulas are already drawn for you. F is our prefix of 2. Ane means single, chained, okay, or single bonded. Rather not single chain, single bonded. So we want to put a carbon to a carbon. Each of these are terminals, so they'll each have 3 hydrogens. So CH3 and CH3. Sometimes you may see these formulas written like this, H3C, CH3. Do you see how the hydrogens are in front of the carbon? That's because they're kind of coming off this side. They're just writing it so it's even more like spatially appropriate. It doesn't matter to me. I'll take either one, but just know you may see them like that sometimes. Heptane. Hept is 7. Ane is single bonds. So I've got to put together 7 carbons. I know the end one's going to have 3 hydrogens. I've got a CH2, a CH2, a CH2, a CH2. Oh, let's stick it together. 1, 2, 3, 4, 5, 6, and then another terminal to give me 7. Ugh, it's a little messy. Okay. So I'm going to tell you right now for the homework, you're going to have to be doing these and it can be a little bit cumbersome with the mastering chemistry. So I would recommend starting the homework now, just so you can get comfortable with the formatting of it. And then if you're having trouble like connecting the carbons and the hydrogens and all that stuff, you can either reach out to me or the tutoring lab is great. They're really comfortable with this homework software, so they can like show you how to connect all the things. You don't want to be stuck Sunday night being like, I know what ethane is and I can't put it in my homework. There we go. Okay. I'm gonna give you one more just because why not? But we are fully good with those before we move into cycloalkanes. Okay, I want you to write a formula for octane, main component in gasoline, and then I want you to tell me what this is. Okay, so write the condensed structural formula for this, just like you did in the last one. And then for this one, tell me what it is. All right, octane. So that means we've got to write 8 carbons. So I've got a terminal carbon, and then we just start chaining together those central carbons until we get to 7 carbons all the way. We want 8, but we need to get to 7. 1, 2, 3, 4, 5, 6, 7, and then the 8th will also be a terminal, so CH3. We're good. Okay, what is the name of this thing? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons, 9 points. Non. They're all single bonded. If you're wondering, well, how would I know if it was double bonded? A double bond would look something like that. Okay, there would be 2 lines next to each other. We will get into that in a little bit. So this is nonane. That's it. Woohoo. All right, so you have started your journey into organic naming. Now let's have a little more fun. So we can have these things known as cycloalkanes. Think of the word cyclo, right? Cyclical. So we have our chain, and it's actually completely connected to itself, making a loop. So over here I have propane. If instead it was all sides connected, we would call it cyclopropane. The formulas are going to be different. Propane has this formula, C3H8. Cyclopropane has a formula of C3H6. The carbon value has changed. I'm sorry, the hydrogen value has changed. The carbon value has stayed the same. This has 3 carbons, so it's prop. This has 3 carbons, so it's also prop. They're all single bonded, so it's ane and ane. Now, what happens when I create a bond here to get to this? Well, if these 2 carbons are bonded to each other, one of these hydrogens has to kind of fall off. So then we can only have 2 hydrogens. That's why this is 2 less hydrogens than whatever its straight chain is. So the cyclical structures will always be 2 less than the straight chains. How you find a cyclopropane hydrogen value is you take the number of carbons in it and you just multiply it by 2, because every carbon only has 2 hydrogens stuck to it. There's no terminals. Does that make sense? So it's important to see that cyclo. The cyclo is going to let you know. Cool. Great. Thank you, Cecilia. So here are some examples of cycloalkanes. Cyclopropane, cyclobutane, cyclopentane. This one we see a lot, cyclohexane. It still honors the number of carbons. So this would be 6 carbons, 5 carbons, 4 carbons, and 3 carbons. The difference being though, there's no terminals. So every single carbon is bonded to another carbon, which means each carbon only is connected to 2 hydrogens. So the formulas will be different. You could draw them like this. I would never ask you to draw them like this. You could draw them like this in the condensed structural formula. You may be asked to do that. Or you could do the skeletal formula where you get these like geometric shapes. Okay, so when you see something like this, what you need to start getting in the habit of is, oh, it's a pentagram. There's 5 points, 5 carbons. Each carbon will have 2 hydrogens. So I want you to name each of these things. These are like straight up skeletal. You're not getting a whole lot out of just the lines. So draw up, down, up, down, up, down, up. Here you've got, well, I'm not going to tell you how many points there are. You can count those. Okay, so this first one is how many points? 1, 2, 3, 4, 5, 6, 7, 8. 8 points. So I know it's oct. They're all single bonded, so I can go with octane. It's not looped in on itself. It's a chain, right? It's not a closed chain. It's an open chain. So we will just go with octane. This one has 1, 2, 3, 4, 5. Make sure you don't double count the point you started at. So if you want, you can even put like an X, like that's where I started counting. 1, 2, 3, 4, 5. So that's pent, all single bonded, ane. The thing I need to add here is I need to say that it's cyclical. So cyclopentane. The formula for this would be 8 carbons, take the 8, multiply it by 2 and add 2. So H18. Cyclopentane, this has 5 carbons. It's really, really difficult to read. 5 carbons. The hydrogens, we just multiplied by 2 to give us 10. We don't have to add the 2 on the ends because there's no end. Okay, name these. So give the correct name for these. I'll give you 2 minutes and then we're gonna move on from naming the basics. Okay, so you've just gotten to the point where you can write them out. We'll just go through them together. So this first one, 1, 2, 3, 4, 4 carbons. What is the prefix for 4? Bute. They're all single chained, butane, not cyclical, so just butane. This one here, how many points? 1, 2, 3, 3 points. So that's pro. They're all single bonded, ane, and it is in a closed chain, so, or a closed circle, so we need to call it cyclo. Cyclopropane. This guy here, 1, 2, 3, 4, 5, 6, 7, 8. Octane. 1, 2, 3, 4, 5, 6. Hex, all single bonded, hexane, and it's cyclo. Cyclohexane. So hopefully, like, I always like organics and teaching people organics because then some of these names that always feel like kind of scary start to make a little bit of sense, right? There's a system to it. So if you see something on the back of, for instance, like a beauty product and it says, oh, it contains cyclohexane. Now you know, okay, well, it is a series of 6 carbons that are connected in a cyclical structure. So you have your basis. Now we're gonna add accessories. Everything we've done thus far has been single chained or cyclical, right? So it's looked like this. All on a single continuous chain. Well, it gets much more complicated. An alkane that has 4 or more carbons. So you won't see this on 3 carbons or 2 or 1. But if it has 4 or more, you can start to have what we call side chains, branches, or sometimes they're called substituent carbon chains, which it means that you have a main chain and then you have a secondary chain coming off of it. So these two structures have the exact same formula, meaning that they're both C4H10. This is also C4H10, but they have 2 different names. This one is butane, right? 4 carbons in a chain. This one is, well, looking at it, the main chain is 1, 2, 3. So that's propane. And then I have a methyl group or a single carbon coming off of the second. So 2-methyl propane. If you're like, what's that? I will show you how to do that system, okay? But these two things for right now have 2 different names. Same formula, 2 different names. Totally can happen. We call this thing a structural isomer. Structural isomers will have the same formula, same molecular formula, but the atoms are arranged in a different way. They have the same number of atoms. So both of these have 4 carbons and both of them have 10 hydrogens. They're just shifted in different ways. These will have different chemical properties. Okay, so you don't just want to say that, oh, you know, these are going to behave in the same way. You have to give them 2 different names. So let's look at, let's saying butane C4H10, this thing here, has 2 structural isomers. So there's the straight chain, and then there's the branched chain. Here, draw 3 possible structural isomers for pentane. So when drawing potential isomers, I would always start by doing the easiest one. So what's the easiest one? The easiest one is just to make it all a single chain. So we've got CH3 bonded to CH2, bonded to CH2, bonded to CH2, bonded to CH3. 1, 2, 3, 4, 5. Okay. Now I want to make a structural isomer. So a structural isomer means that it's actually a different compound. It doesn't mean that I'm just going to like move this thing and write it down here like this and then get rid of that. That is still a single chain. I need to change the fact that it is a single chain. So one way to do that is, why don't we make the chain 4 and take this N thing and stick it somewhere in the middle. So CH3, CH2, CH2, CH3. And then I'm going to take what was this end thing, I'm going to stick it somewhere in the middle. So let's put it here, CH3. But if I stick it here, look at this carbon. This carbon has to drop one of its hydrogens because it's got now 1, 2, 3, 4, 5. So I am going to actually erase that hydrogen. It no longer has 2 hydrogens. It only has 1 hydrogen. If I'm going to make another isomer, sometimes people will take this and they'll just say, oh, I'm just going to move it over here. That isn't a structural isomer. That's just me taking this same thing and rotating it around, right? Instead of it being 1 in from the left, it'll be 1 in from the right. But I just take the whole thing and just spin it and we're back at the same thing. So what I'm going to do instead is take another one of these end carbons and I'm going to stick it in the center. Okay, so let me see how they've got it. So we've got the single chain. Then we've got the branched one. That's the one we just drew. Then what we could do is take another one of these and stick it on that central carbon so that we get this fun structure over here. What happened to that carbon that was in the center? We had to take that hydrogen. And you can kind of think of that hydrogen as moving over here. So this hydrogen moved here to make room for this carbon to connect there. So now we've got a carbon in the center that doesn't have any hydrogens because it doesn't have any spaces. This carbon in the center is connected to 4 other carbons. All of these carbons end up being terminal. Some examples of things that are not structural isomers. People will write things like this. Okay, so they'll go CH3, CH2, CH2, CH3, and you know, there's another carbon that we're going to stick somewhere. So they'll stick it here and they'll say, CH3. Okay, I know I got to drop this down to 2 because it's got a new spot. Is this different than this? No, it's the same thing. We've just put the kink in it. But remember, these are all single bonds, so it can rotate. So this is the same thing as this. It's not just like sort of the same, it's the identically the same thing. So that is not a structural isomer. A structural isomer is where you actually change the arrangement of the atoms. So Cecilia, so they need to be added in the middle of the chain. Yes, because what happens if I take this and I add it here, I'm just adding it to the end of the chain. It wasn't it at the end of the chain already, right? So yeah, it's got to be somewhere in the center. So let's do C6H14, right? Really quickly, just do lines, the structural isomers. I'll do the first one for you. 1, 2, 3, 4, 5, 6. So you should be able to draw 4 other structures. There's a total of 5 structural isomers. Okay, so I've got this structure here. I'm going to take the carbon at the end and I'm going to add it here. All right, so first structural isomer, instead of having a chain of 6, I'll have a chain of 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. And I'm going to put a branch off of this first one. So there's a carbon here, 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 and here, and then there's the carbon sticking off of here. If you had drawn it over here, that's the same as this. So this or this. 1, 2, 3, 4, 5, and you could have put it off of this end. Those are the same thing. What isn't the same thing is, well, what if instead of putting it in here, I put it in the center? That actually is a different structure. So 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, and instead of that, I put it off of here. We could say that's a different structure. So we've got what? 1, 2, 3. Another one is I could put 2 on this first thing. So take another one of these off and stick it there. So the chain would now be, instead of 5, it'll be 4. So 1, 2, 3, 4. So it would be 1, 2, 3, 4. And then I'd put 1 chain here and I could put 1 chain here. So 2 on this one. That's 4. And then the 5th one, well, what if instead of having it here, I put 1 on this guy and then 1 on this guy? So it would be a chain of 4, 1, 2, 3, 4, and I put 1 here and 1 here. Okay, those are all the possible structural isomers. Things that aren't structural isomers. say you have, so we'll do it in red, not. This 1, 2, 3, 4, and you're like, oh, well, I'll put a chain here and a chain here. What's that? That's the original one, right? 1, 2, 3, 4, 5, 6. You don't add it to the end. Doing this, so 1, 2, 3, 4, and saying, well, I'm going to put the 2 on this side. That is the same thing as this thing, right? It's just rotated over. So you've got to start to think about it as like, I can take these molecules and move them in space. If I can move it to make it match another one, it's no longer an individual structural isomer. It's just a repeat of an old one. Any questions on that? Okay, so each of these things will have its own name. So how do we name accessories, as I like to call them? So substituents or accessories are atoms or groups of atoms that attach to a carbon chain, and they include what's known as an alkyl group or a halo group. An alkyl group is a group of carbon atoms attached to the original carbon chain. You name them by classifying how many carbons they have. So how many carbons are in that chain. The carbon chain, the little limb that's sticking off. Thus far, we've only done like 1 carbon sticking off, but you could have 2 or 3 or whatever. You use the IUPAC system. So if it's 1 carbon, it's meth. If it's 2 carbons, it's eth, so on and so on. You YL the name. So if it's a single carbon, which is sort of what we saw back with all of these, right? This is a single carbon. So we would say that that's a meth. And then we go YL. The YL lets you know that it's not on the main chain. It's a secondary chain. So this would be a methyl group. This and this are also methyl groups. This is one methyl. This is another methyl group. Trying to think what else I'm going to say about that. If again, yeah, if it's 2 carbons, it would be like a propyl group. Sorry, a butyl, an ethyl group. Three carbons would be a propyl group, and so on. A halo substituent or a halo accessory would be anything from that 7th column. So fluorine, chlorine, bromine, iodine, fluoro, chloro, bromo, iode. So here are some of the accessories. You see this one here. This is just a single carbon, methyl. This is 2 carbons, ethyl, 3 carbons, propyl. Again, why are they getting the YL ending? Because they are not the main chain of carbons. They are an accessory. The main carbon chain should always be your longest carbon chain. Okay, main chain equals longest. This thing here is known as isopropyl. It's isopropyl because it's 3 carbons, but it's attached in the center. Here, the regular propyl is attached at the end. We don't do a whole lot of work with isopropyls or isols, but no, that's what it is. All right, these accessories, fluoro, chloro, bromo, iodo. So you name your longest chain and then you add the accessories. Let's decide how to add these accessories. So when writing an alkane with substituents, write the alkane name for the longest carbon chain. So you first find your longest carbon chain and you name that. Number the carbon atoms in such a way that you start from the end nearest the accessory or the substituent. You have to give the location of the name for the substituent, write it in alphabetical order, and you put it as a prefix in the front of the main chain. I feel like it's easier to just look at this. So let's look at this thing here. So where is the longest chain? Obviously, this here is the longest chain. Do you see any accessories? Do you see anything on here that is different from what we've done thus far? Yeah, I see 2 different things. This here is an accessory, and this here is an accessory. So we will have to name those or include those in the name. When working on this, I always name my longest carbon chain first, and I kind of write that as far over to the right as possible so I have space to put other things or the accessories in front. So this is 1, 2, 3, 4, 5 carbons. So 5 carbons is pent, and they're all single chained, right? So this is going to be pentane. Let me see what time it is. I know we're getting, okay, we've got 1 minute. I just want to go over this real quick so you have it. Pentane. So now I need to put the accessories in, well, I need to number it first. So I'm going to number it in such a way that these accessories fall on the lower number carbons. So I'm going to go 1, 2, 3, 4, 5. This is going to be carbon 1. This is going to be carbon 5. I wouldn't number it in the other direction because if I number it this way, this falls on carbon 2 and this falls on carbon 3. If I numbered it in the other direction, 1, 2, 3, 4, 5, this would fall on carbon 3. This would fall on carbon 4. We always want the accessories to fall on the lowest carbon number. But no, it isn't always numbered left to right. Sometimes the accessories are stuck on this end and you want to actually have this as carbon 1. So I've got 2 accessories here, one on carbon 2 and one on carbon 3. This is a methyl and this is a chloro. So you list them in alphabetical order. Chloro comes before methyl in the alphabet. So I'm going to name my chloro first. So this is chloro. What carbon is it on? It's on carbon 2. So it's going to be 2-chloro. Dashes go between numbers and letters. Okay. So 2-chloro dash 3 methyl. And then this just gets smushed together with that. So 2-chloro dash 3 methyl pentane. The dashes go between numbers and words. So we've got a word and a number. That's why we've got a dash. Oh, sorry, there should be a dash here. Commas go between numbers, and I'll show you that a little bit later. So 2-chloro dash 3 methyl pentane. Blech. Here we go through the slides. You name the longest chain first, then we add our accessories, 2-chloro, 3-methyl pentane. Questions on that? Conceptually, not, I need to practice this a whole bunch.
Are the accessories always going to be directly next to each other, or will you see one on 2 and one on?
You could have 2 on the same carbon. So you could have a methyl group here and a methyl group here, and we'll talk about how to number and name those. They're not necessarily next to each other. You could have had a chlorine here and a chlorine over here. Okay. Yeah, it could be in a bunch of different places. Again, always numbering the carbons so that your accessories get the lower number. We will do a bunch more practice with this on Thursday, so don't stress about practice. We will practice some more. All right, so we're done for today. I will see you all Thursday. If you have any just general questions, feel free to throw your mute off and you can ask me. If you have any personal questions, stay around and I will help you out where I can. Have a good day. Hey, Amber, it's just you and I. Do you have a question? Okay, well, if you do, just send me a message through email.